Next up, we're going to just talk about how this factor that makes equations exact actually works. So sort of let's think about for mu equal to whatever we end up using. The equation mu times m dx plus mu times n, and I'm going to go back to just saying like a generic y equal to 0. That equation, where we multiply everything through by mu, is exact. Or by the definition of exact, it means that if we take the partial derivative with respect to y of mu times m, which would be mu sub y times m plus mu times m sub y, we should have that that's equal to the partial derivative with respect to x of mu times n. So that's mu sub x times n plus mu times n sub x. So these two being equal is just the definition of exact. And oops, I forgot to get rid of that last one. And then these two formulas just come from taking the product rule derivative of mu times m or mu times n. So then what we're going to do is we're going to think about this sort of first case. So we're going to think about if mu only depends on x. But if we right here said suppose mu only depends on y, then we would kind of follow similar steps. So suppose mu only depends on x. Then mu sub y is equal to 0. And we need mu sub y times m plus mu times m sub y equal to mu sub x times n plus mu times n sub x. And that term is going to go to 0 since mu sub y is 0. And so I have mu times m sub y minus mu times n sub x is equal to mu sub x times n. Or mu times m sub y minus n sub x divided by n is equal to mu sub x. And then kind of here, it's going to be important to note that mu sub x is d mu dx. So really what I have, that d mu dx is equal to mu, actually it'll look even better this way, it's equal to m sub y minus n sub x over n times mu. So now I'm going to kind of remember that every time I have d dx of e to some stuff, that derivative is d dx of some stuff times e to the power of some stuff. That's a property of derivatives that you should be familiar with from calculus, and it always keeps coming back up. So I think mu should be equal to e to the power of this stuff integrated if I want it to satisfy this rule. And then that's exactly what we got here. E to the integral of m sub y minus n sub x over n dx is what mu is. And kind of at the start of this like special calculation of mu, I said suppose mu depends only on x. If you said suppose mu depends only on y, the same thing would happen. It's just that you would end up with that other equation. And I'm not going to do that because it's sort of repetitive. And this hopefully gives you the intuition for how the whole factor works in either case. So with the little bit of time that I still have left to talk about this section, I thought it'd be good to sort of recap the most important things to be careful about when you're doing these exact equations. So I'm going to say it's a quick recap of tricks, but they're not really tricks. They're just things we have to be really careful about. So first of all, I guess formatting and exact equations are important. And so just always make sure you start a problem by checking that. If you're working on one of these problems, like let's say you did this one, and you forgot about this checking exactness thing, then you would start integrating a whole bunch of stuff and generate a solution. And you might never realize that you can't build a solution that way. And if you do, you could sink a lot of time into it. So always check exactness really early on, because it changes the problem entirely if you have to build that factor and multiply it through. When we were working on our first example, I'm so sorry if you can hear that. The cat's upset because he hasn't gone for a walk today. So when we were working on this first example, let's see, where did I write it? Right here. We said that one of the challenging things here is just that there's a lot to keep track of. So there's a lot to keep track of. When you're working on your homework, that doesn't matter so much, just sort of do it however works for you. But if you're turning this in on an exam, what's going to help you is to just write everything out. The reason I say that is because if you mess something up, I can see that you understood the things that you were trying to build, even if something goes wrong. If you try to jump right to f is equal to, let's see, it's equal to the integral of m dx plus, and then that big gross formula for g. See, you do integral n minus d dy integral m dx. So, let's see. So if you do that all in one line, that's not good. Instead, just do f is equal to some stuff. So g is equal to some stuff. So g prime is equal to some stuff, and g is the integral of that stuff. So f is equal to that plus that plus that is equal to c. Follow that step like one at a time. That way it's clear what goes wrong if something goes wrong. So do that. Don't do that other thing. And then in the second example, I said the tricky thing is to make sure you have only one unknown constant. So there's going to be a temptation to be very careful about this. When you take your integral of g, you're used to always saying plus a constant. That's fine. Sometimes I don't do it because I'm a little bit lazy. So if you have g equal to some stuff plus a constant, combine it, when you set f equal to some other constant. And then sort of a other thing to remember, sometimes you all will just forget that you need to set f equal to that constant. Sort of otherwise, how do you solve for y? which is the goal of this whole exercise. It goes on for so long that you might forget that, but that is what we're trying to do. So those are the things that I think tend to go wrong here. Next up is going to be our wrap up, where I just say everything we covered and give you your practice problem.